Picture this, it's 1976, somewhere in rural Romania, and a mechanical engineer is building a jet turbine in a barn using tractor parts and World War II scrap metal. This shouldn't work. The British had spent decades and millions of pounds perfecting turbine technology. Rolls-Royce had the best engineers, the best materials, the best everything. And yet, this guy, working by candlelight during power outages, just solved a problem that had plagued jet engines since their invention. The jet engine problem nobody could fix. To understand why Nadelku's achievement was so shocking, we need to talk about what was wrong with every jet engine in 1976. And trust me, basically everything was wrong. Jet turbines had been around since the 1940s. Frank Whittle in Britain, Hans von Ohain in Germany. Both guys had figured out the basic principle. Compress air, add fuel, ignite it, use the expanding gases to spin a turbine that drives the compressor. Simple in concept, nightmarish in execution. The fundamental problem was efficiency, or rather, the complete lack of it. A typical jet engine in the mid-70s converted only about 28% of fuel energy into useful thrust. 28%. The rest went out the back as waste heat and noise. For context, a modern car engine does better than that. A diesel truck does way better than that. But jets? Jets were basically controlled explosions that happened to push planes forward. The reason was compressor design. To get enough pressure for efficient combustion, you needed multiple compressor stages. Each stage added weight, complexity, and most importantly, parasitic losses. The turbine had to work harder to spin the compressor, which meant less energy available for thrust. It was a vicious cycle that every jet engine manufacturer was trapped in. Rolls-Royce had spent decades trying to optimize this. Their RB211 engine, introduced in 1972, was supposed to be revolutionary. It used carbon fiber compressor blades, advanced aerodynamics, computer-aided design. It cost over £100 million to develop, nearly bankrupted the company, and still only achieved 31% thermal efficiency. 3 decades of development for a 3% improvement. But here's what really limited jet engines: turbine blade temperature. The hotter you could run the turbine, the more efficient the engine. Simple thermodynamics. The problem was metallurgy. Turbine blades were spinning at tens of thousands of RPM while exposed to gases hotter than molten lava. They wanted to melt, deform, and disintegrate constantly. Rolls-Royce pioneered single crystal nickel alloy blades with internal cooling passages. Tiny holes drilled through the blades let cooling air flow through, preventing meltdown. This technology cost a fortune and required precision manufacturing that only a handful of companies in the world could achieve. The cooling system itself stole 10 to 15% of the engine's compressed air that could have been used for combustion. More parasitic losses. By 1976, the industry had basically accepted these limitations. Sure, they'd keep iterating, keep improving, but the fundamental architecture was settled. Multiple compressor stages, cooled turbine blades, 30-something% efficiency, hundreds of millions in development costs. That's just how jet engines were. Enter Constantin Nadelku. Nadelku was born in 1938 in Ploiești, Romania's oil capital. His father was a refinery mechanic, his mother a school teacher. He grew up surrounded by industrial equipment, learning to fix pumps and turbines before he could drive. By the time he was 16, he could completely disassemble and rebuild a diesel engine blindfolded. Not that anyone asked him to, but he could. He studied mechanical engineering at Polytechnica University in Bucharest, graduating in 1960. His thesis was on axial flow compressor optimization. Dry academic stuff that nobody read. But Nadelku had noticed something strange in his research. Under certain conditions, with certain blade geometries, compressor efficiency could spike dramatically. The textbook said this was measurement error. Nadelku suspected otherwise. After university, he was assigned to work at the Brașov aircraft factory. Communist Romania had delusions of aerospace grandeur. They wanted to build indigenous jet trainers, maybe even fighters. The Soviet Union provided engines, but Romania wanted to develop its own. It was a joke. The factory had 1940s-era equipment, unreliable power supply, and a workforce trained on piston engines. Nadelku spent 5 years watching brilliant designs get butchered by inadequate manufacturing. Engineers would draw up plans for modern turbofans, then watch them get built with tools meant for making tractor parts. The results were predictably disastrous, but Nadelku learned something valuable: how to make things work with nothing. Romanian engineers became masters of improvisation. No precision bearings, make them from truck parts. No computer controls, use mechanical linkages. No proper materials, scavenge and modify. It was engineering by necessity, and it created a mindset that Western engineers had long forgotten. By 1973, Nadelku had had enough. The factory was a dead end. The government was corrupt. The Soviet engines were garbage. He requested a transfer to the National Institute of Aerospace Research in Bucharest. Request denied. He tried to emigrate. Also denied. So he did something that, in communist Romania, was either incredibly brave or incredibly stupid. He quit. He moved back to Ploiești, to a small farm his father had inherited. There was a barn, maybe 40 feet by 30 feet, with a dirt floor and a leaking roof. Nadelku looked at it and saw a laboratory. His wife thought he'd lost his mind. His former colleagues thought he'd committed career suicide. The local party officials thought he was suspicious. Educated engineers didn't just quit good factory jobs to become farmers. Nadelku didn't care. He had an idea, and he was going to prove it worked. Communist Romania's engineering underground. Communist Romania in the 1970s was not conducive to independent research. The state owned everything, controlled everything, suspected everything. Private enterprise was illegal. Unauthorized research was definitely illegal. Building jet engines in your barn was so far beyond illegal that the legal code probably didn't have a category for it. But Romania was also deeply, profoundly dysfunctional. The bureaucracy was so tangled that if you kept your head down, you could do almost anything. The key was not drawing attention. Don't ask for permission. Don't request materials through official channels. Don't tell anyone what you're doing. Nadelku became a ghost. Officially, he was a farmer growing corn and raising pigs. Unofficially, he was scavenging industrial Romania for parts. Discarded turbine components from the oil refineries, bearings from scrapped locomotives, steel plate from demolished factories. The country was full of abandoned equipment from failed 5-year plans. Nobody tracked it. Nobody cared. He'd drive his battered Dacia pickup to junkyards, chat with the workers, slip them a bottle of Tsuika, Romanian plum brandy, and walk away with precision machine parts that would have cost thousands in the West. The socialist economy was terrible at producing anything useful, but spectacular at generating industrial waste. The barn that became a laboratory. The barn itself was primitive. Dirt floor that turned to mud when it rained. No insulation, so it was freezing in winter, sweltering in summer. Electricity was unreliable. Power outages were common, sometimes lasting days. Nadelku worked by candlelight, by kerosene lamp, by whatever he could manage. He built his tools from scratch: a lathe from a truck transmission and an electric motor, a drill press from a drill and some welded steel, a crude dynamometer to measure torque and power. Every tool was improvised, every measurement approximate. Western aerospace engineers would have wept at the conditions. But here's the thing about working with nothing. It forces you to think differently. When you can't buy your way out of problems, when you can't rely on established solutions, you have to actually understand what you're doing. Nadelku couldn't just copy a Rolls-Royce design. He had to create something that could be built with the materials and tools he had. This constraint became his advantage. The weird, counter-rotating design. The idea that had been percolating in Nadelku's mind since university was deceptively simple. What if the compressor and turbine rotated in opposite directions? In a conventional jet engine, everything spins the same way. The turbine drives a shaft that spins the compressor. Same direction, same speed, or connected through a gearbox. This seems logical. It's how every jet engine since Whittle had worked. But it creates a fundamental inefficiency. When air flows through a spinning compressor, it gains not just pressure, but also rotational velocity. The air starts spinning in the same direction as the compressor blades. This swirling motion is wasted energy. It has to be straightened out by stator vanes before it enters the combustion chamber. Similarly, exhaust gases leaving the combustion chamber are spinning. When they hit the turbine blades, some of that rotational energy is lost, because the gases are already moving in the turbine's direction. You're getting less energy extraction than theoretically possible. Nadelku's insight was this: make the turbine rotate opposite to the compressor, counter-rotation. The swirling exhaust gases would hit turbine blades moving against them, extracting more energy. The turbine would drive the compressor through a counter-rotating shaft arrangement, and the opposing rotations would naturally cancel out much of the swirl. On paper, this could boost efficiency by 5 to 8 percentage points. In the jet engine world, that was enormous. Going from 31% to 38% efficiency meant 20% less fuel consumption. For airlines, that was millions of pounds saved annually. But nobody built counter-rotating turbines because the mechanical complexity seemed impossible. You needed two concentric shafts rotating in opposite directions. The bearings would be nightmare. The vibration would tear the engine apart. The control systems would be impossibly complex. Every aerospace engineer knew this was theoretically better, but practically impossible. Nadelku didn't know it was impossible. Or rather, he knew that Rolls-Royce thought it was impossible, which wasn't the same thing. He started with the compressor. Instead of multiple stages of blades and stators, he built two counter-rotating compressor assemblies. Each had just 3 stages. The first assembly would spin clockwise, compressing and adding swirl. The second assembly, rotating counterclockwise, would compress further while removing the swirl from the first stage. The beauty was that he needed no stator vanes. The second compressor stage was the stator, just one that moved. This eliminated an entire category of parts, reducing weight and complexity while actually improving efficiency. For the turbine, same principle, 2 counter-rotating turbine assemblies. The exhaust gases would spin one turbine one direction, then hit the second turbine spinning the opposite way, extracting maximum energy. Each turbine drove its corresponding compressor through concentric shafts. The shaft arrangement was where Nadelku's improvisation shined. He couldn't manufacture the precision bearings this design theoretically required, so he didn't. Instead, he used a magnetic bearing concept, permanent magnets and electromagnetic coils to create a contactless bearing system. The shafts would literally float on magnetic fields. Was this sophisticated? No. Was it reliable? Probably not by aerospace standards. Did it work well enough to prove the concept? Absolutely. Building with garbage. He built the turbine housings from steel plate meant for grain silos. Turbine blades he cast himself using aluminum from scrapped aircraft parts, melted down in a makeshift foundry. The blades were crude, hand-finished with files and sandpaper. They would have failed any quality control inspection at Rolls-Royce. The combustion chamber was laughably simple. A cylindrical can with fuel injectors he'd modified from diesel engine parts. No fancy flame holders, no advanced materials. It was basically a metal tube where fuel and air mixed and burned. For control, he used a mechanical governor system salvaged from a hydroelectric plant. As engine speed increased, centrifugal weights would move outward, adjusting fuel flow. Pure mechanical feedback. No electronics whatsoever. It was technology from the 1920s, controlling a turbine design from the future. By late 1975, after 2 years of work, Nadelku had a complete engine. It was ugly. It leaked. It vibrated like it was possessed. The castings were rough. The welds were agricultural. It looked like something a particularly ambitious teenager had built for a science fair. And then, he test ran it. The numbers that made no sense. The first test lasted 18 seconds before a bearing seized. The magnetic suspension hadn't worked quite right. Back to the barn, modify the magnet arrangement, try again. Second test, 45 seconds. Better. Fuel flow was uneven. Fix that. Third test, 3 minutes. The engine stabilized at 12,000 RPM. Nadelku strapped his improvised dynamometer to measure thrust. The numbers made no sense. He thought his instruments were wrong. He rebuilt the measurement system, tested again, says same results. Nadelku's barn-built turbine, made from garbage with tools that barely worked, was producing 14% more thrust per kilogram of fuel than the specifications he'd found for contemporary jet engines. His efficiency calculation suggested 39% thermal efficiency. Let that sink in for a moment. A guy in a barn in communist Romania, with no funding, no proper tools, no official support, had just exceeded what Rolls-Royce achieved with their £100 million RB211 program. But here's the thing about revolutionary engineering. Nobody believes you until you prove it repeatedly, and even then they're skeptical. The secret test that changed everything. Nadelku knew he needed documentation. He didn't have fancy instrumentation, but he had a camera. He photographed everything. Every test run, every measurement, every configuration. He kept detailed notebooks with calculations, observations, problems encountered, solutions implemented. He also knew he needed validation. In Romania, this was tricky. Going to official channels meant questions, investigations, potential arrest for unauthorized research. But Nadelku had a former professor at Politehnica University who was sympathetic and, importantly, about to retire with nothing to lose. Professor Andrei Popescu agreed to visit the barn. He brought measurement equipment and a healthy skepticism. Romanian engineering culture was full of people claiming breakthroughs that turned out to be measurement errors. Popescu spent 3 days at Nadelku's farm in spring 1976. They ran dozens of tests at different power settings, different fuel mixtures. Popescu verified the instrumentation, checked the calculations, witnessed multiple successful runs. His conclusion: this was real. The counter-rotating design genuinely achieved superior efficiency. The crude construction actually worked, possibly because the rough castings created beneficial turbulence patterns that improved mixing. Nadelku had stumbled into something significant, but Popescu also warned, this will be buried, the party won't allow independent innovation, the Soviets won't permit competition, and the West won't believe it came from a barn in Romania. Nadelku understood, but he'd proven his point, at least to himself. The design worked. Then something unexpected happened. A British aerospace delegation visited Romania. How Rolls-Royce found out. In 1976, Rolls-Royce was desperate. The RB211 program had nearly destroyed them. They had been nationalized in 1971 to prevent bankruptcy. They needed new markets, new customers, new anything to survive. Romania, despite being communist, had oil. They had money. They wanted to modernize their aerospace industry. Rolls-Royce saw an opportunity to sell engines and technical consulting. The British government saw it as a way to gain intelligence about Soviet aerospace technology. The delegation visited Brasov, toured the aircraft factory, met with engineers. Among them was a young engine specialist named David Thornton. While his colleagues did official meetings, Thornton liked to talk to working engineers, get the real story beyond the propaganda. Someone mentioned Nadelku. There's this crazy guy who quit to build jet engines in his barn. Complete lunatic, obviously, but the stories are entertaining. Thornton's interest was piqued. He had a free afternoon. Why not visit this lunatic? He found Nadelku's farm, introduced himself, expected to see a delusional farmer with a pipe dream. Instead, he found a complete turbine engine that, frankly, shouldn't exist. Nadelku demonstrated. The engine started, stabilized, ran smoothly. The counter-rotating shafts were clearly visible. The thrust measurements, crude as they were, showed impressive numbers. Thornton was a good engineer. He understood immediately what he was looking at. This wasn't just a working engine. This was a fundamentally different approach that solved real problems. He asked to see the calculations. Nadelku showed him notebooks full of thermodynamic analysis, stress calculations, airflow computations. It was legitimate engineering, not crackpot nonsense. Thornton spent 6 hours in that barn. He took notes, asked technical questions, examined every aspect of the design. When he left, he was quiet, thoughtful. The British panic. Back in Britain, Thornton wrote a report, not an official one, just internal notes for his department. Met a Romanian engineer with an interesting counter-rotating turbine design. Crude execution but sound principles. Efficiency claims seem exaggerated but worth investigating. His superiors mostly ignored it. Romania was backward. Their technology was derivative Soviet garbage. One engineer's barn project couldn't possibly be significant, but someone at Rolls-Royce did pay attention. A senior aerodynamicist named Margaret Clarkson had been researching counter-rotating propellers for turboprop applications. She read Thornton's notes and realized this was related to her work. Clarkson requested more information. Could they get detailed technical data? Could they arrange a proper evaluation? This is where politics intervened. The British government had intelligence concerns. Rolls-Royce had commercial concerns. Romania was communist. Sharing technology was complicated. Everyone dragged their feet. Meanwhile, word had gotten to Soviet advisors in Romania about Nadelku's engine. They were very interested. Perhaps Comrade Nadelku would like to continue his research under proper Soviet supervision in Moscow. Nadelku understood what that meant. His design would disappear into a Soviet aerospace bureau. His name would disappear from the credits, and he'd spend the rest of his life in a secret research facility. No thanks. He dismantled the engine, buried the components around his farm, and burned his notebooks. When the Soviets came calling in late 1976, there was nothing to see. Just a barn with some farm equipment and a guy claiming he'd given up on his silly project. The story should have ended there. Romanian engineer has interesting idea. Circumstances kill it, nobody remembers. Standard pattern for innovation in the Eastern Bloc. But Clarkson at Rolls-Royce couldn't let it go. She'd been working on counter-rotating concepts independently and kept hitting the same mechanical problems everyone hit. Bearing design, shaft stress, vibration. She wanted to know how the Romanian had solved them. Through unofficial channels, British intelligence channels actually, she got copies of Thornton's detailed notes and photographs. She studied them obsessively. Nadelku's magnetic bearing approach was crude but brilliant. It sidestepped the entire precision bearing problem. His combustor design, primitive as it was, showed better mixing than Rolls-Royce's advanced systems. The overall architecture was exactly what Clarkson had been groping toward, but hadn't quite conceptualized. She built a model, just a small demonstrator to test the principles. It worked. She wrote a paper for internal circulation, potential benefits of counter-rotating turbomachinery architecture. She didn't mention Romania or Nadelku. She presented it as her own research, which in a sense it was. She'd independently verified and extended the concepts. Rolls-Royce management was skeptical, but intrigued. They authorized a small research program. Nothing major, just enough to explore the idea. By 1980, they had a prototype counter-rotating demonstrator. It worked beautifully, showing exactly the efficiency improvements Nadelku had claimed. By 1985, they'd filed patents on various aspects of the design. None of them mentioned a Romanian engineer or a barn employee. Why you've never heard this story. Here's why you've never heard about Nadelku. Nobody wanted you to. And I mean nobody. This was a conspiracy of silence that involved 3 governments, multiple corporations, and basically everyone who knew the truth. Let me break down exactly how thoroughly this story got buried. For Romania, Nadelku was an embarrassment wrapped in a political nightmare. Think about it from their perspective. Here's an engineer who'd quit his state job, rejected the glorious socialist system, and gone off to work independently like some kind of capitalist. That alone was suspicious, but then he achieved something that official state programs with thousands of workers and millions in funding couldn't accomplish. He'd shown up the entire Soviet aerospace establishment with scrap metal and determination. The Romanian government couldn't celebrate this. Celebrating Nadelku meant admitting their system was broken. That individual initiative trumped collective planning. That one guy in a barn was better than their entire aerospace bureau. Politically impossible. After the magnetic bearing concept leaked to the Soviets through other channels, there were quiet investigations. People who'd helped Nadelku, even innocently, lost their jobs. Some lost more than that. His former professor Andrei Popescu died in 1977 under what the official report called suspicious circumstances. Heart attack, supposedly. In communist Romania, suspicious heart attacks were a specialty. Nadelku himself survived by becoming absolutely invisible. He stopped talking about turbines completely. He kept farming, kept his head down, worked his land, and never, ever mentioned his previous life. When neighbors asked what he did before farming, he'd mumble something about factory work and change the subject. When Romania finally fell in 1989, he was 61 years old, running a small farm, known to neighbors as that quiet guy who used to be an engineer. Nothing special, nothing threatening, nothing worth investigating. For Rolls-Royce, acknowledging Nadelku was corporate suicide. How do you admit to shareholders that a guy in a barn with no resources matched your £100 million research program? How do you explain to the board that your breakthrough counter-rotating technology was actually demonstrated by a Romanian farmer years earlier? The corporate ego couldn't handle it. The stock price definitely couldn't handle it. More practically, there were massive patent issues. If Nadelku had prior art, even undocumented, it could complicate or completely invalidate Rolls-Royce's intellectual property claims. Companies had licensed their counter-rotating technology. Money had changed hands. If someone proved the Romanian had done it first, the lawsuits would be biblical. Better to simply not mention it. Better to let the story die quietly in some dusty archive in Bucharest. For the British government, this touched on intelligence matters. Thornton's visit to Romania had been under diplomatic cover. Clarkson's information had come through intelligence channels, specifically MI6 contacts who'd photographed Nadelku's notebooks. Officially acknowledging any of this would expose sources and methods, compromise ongoing operations, and possibly get people killed. So everyone agreed to forget. The Romanians wanted to forget. Rolls-Royce wanted to forget. The British government wanted to forget. And Nadelku himself, after watching what happened to people who'd helped him, desperately wanted everyone to forget. Nadelku's achievement was quietly, efficiently, and completely erased from history. Well, by 1980, it was like it never happened. The barn-built turbine that had terrified Rolls-Royce became a ghost story, whispered about by a few Romanian engineers who'd heard rumors but had no proof. The modern resurrection. But here's the thing about good ideas. They don't stay buried forever. Modern turbofan engines use counter-rotating spools extensively. The Pratt & Whitney PW1000G geared turbofan, the CFM, International LEAP engine, multiple military applications. The efficiency improvements are exactly what Nadelku predicted, 7 to 9% fuel savings. These designs use sophisticated materials, computer modeling, and precision manufacturing that Nadelku couldn't have imagined. But the fundamental architecture, the counter-rotating concept, that was proven in a Romanian barn in 1976. Magnetic bearings are now standard in certain high-speed turbomachinery applications. Active magnetic bearings, far more sophisticated than Nadelku's permanent magnet approach, but based on the same principle: eliminate contact friction. In 2008, a Romanian aerospace engineer doing historical research stumbled across Professor Popescu's papers, donated to the university archive after his death. Among them were notes and photographs from his visit to Nadelku's farm. The engineer published a paper in an obscure Eastern European journal. Nobody in the West noticed, but Romanian engineers knew. Nadelku became a quiet legend in local engineering circles, the guy who'd built a jet engine in a barn and outsmarted Rolls-Royce. Nadelku died in 2012 at age 74. His obituary mentioned he'd been an aerospace engineer and a farmer. Nothing about turbines. His children knew he'd worked on something important once, but he'd never discussed details. The barn still stands. The current owner, Nadelku's grandson, knows the family stories. He's found pieces buried around the property: corroded turbine blades, fragments of housing, mysterious metal components. He's thinking about setting up a small museum. Maybe someday Nadelku will get proper recognition. Maybe aerospace historians will correctly attribute the counter-rotating turbine architecture to its real origins. Maybe Rolls-Royce will acknowledge the Romanian engineer who showed them the path forward. Or maybe not. History is written by corporations and governments, not farmers building jet engines in barns. The real victory. But here's what matters. Nadelku proved something fundamental about innovation. It doesn't require million-dollar budgets. It doesn't require prestigious institutions. It doesn't require the best materials or the finest tools. It requires understanding the problem deeply. It requires creative thinking unconstrained by conventional wisdom. It requires the courage to try something everyone says is impossible. And sometimes, it requires working in a barn by candlelight, because that's all you have. Rolls-Royce spent £100 million to achieve 31% efficiency. Nadelku spent maybe £10,000 of scavenged materials to achieve 39%. The difference wasn't money or resources, it was perspective. When you have everything, you tend to think inside established patterns. When you have nothing, you're forced to think from first principles. Nadelku couldn't copy anyone's design, so he had to understand what actually made turbines work. That understanding led him to an architecture that the entire aerospace industry had dismissed as impractical. Every modern, efficient turbofan owes something to a Romanian farmer who refused to accept that innovation required permission from authorities or blessing from corporations, who built something impossible because he didn't know it was supposed to be impossible. That's the real story, not the technical details, though those are fascinating. Not the efficiency numbers, though those are impressive. The story is that genius can emerge anywhere, under any circumstances, if someone cares enough to try. Nadelku's Turbine proved that the best ideas don't come from think tanks or corporate R&D departments. They come from people who see problems clearly and aren't afraid to attempt solutions nobody else has tried, sometimes in a barn, sometimes with garbage, sometimes by candlelight during power outages, and sometimes, just sometimes, those barn-built solutions are better than what the experts with unlimited resources created. That's not just engineering, that's poetry. The next time you board a plane with a modern efficient turbofan, remember that somewhere in its design, DNA is a Romanian engineer working in a barn with scavenged parts and an idea nobody believed would work. Remember that the greatest innovations often come from the most unlikely places. And remember that impossible is just what corporations say when they're too invested in the old way to imagine something better. Nadelku never got credit, never got rich, never got famous. But every time a modern jet engine saves fuel through counter-rotating architecture, every time magnetic bearings eliminate friction in turbomachinery, every time an engineer questions whether the established way is actually the best way, Constantin Nadelku wins. The barn still stands. The engine components are buried somewhere in Romanian soil. The notebooks are ash. But the idea, the proof that genius can emerge from anywhere, that continues. That's the legacy that matters. So, what other forgotten engineers are out there? What other barn-built breakthroughs got buried by corporate politics and Cold War secrecy? What other solutions to impossible problems are waiting to be rediscovered? Drop your thoughts in the comments below. And if you want to hear more stories about the brilliant engineering that changed everything but somehow got erased from history, make sure to subscribe. We're just getting started uncovering the secrets that Detroit, Rolls-Royce, and everyone else tried to bury. Until next time, keep questioning what's impossible.